So, I have given, hello sir, good evening. I have given you the permissions.
Okay, can you hear
So,
me?
yeah,
Yes, sir.
Okay, okay, thank you, thank you. Let me know when to start. Huh?
Yes, sir. I'll give a short introduction and then we can start.
Okay, okay.
Yes. Okay. Thank you all for being here for this session. We'd like to warmly welcome our speaker, Dr. Sankarasubramanian, from the Space Astronomy Group at the UR Rao Satellite Center, ISRO. Dr. Shankar is a prominent scientist specializing in X-ray astronomy with a particular focus on solar observations. His research has significantly contributed in understanding of the sun's high energy phenomena and the dynamic processes occurring in its atmosphere. Dr. Shankar's work is crucial for advancing solar physics and improving our knowledge of solar activity and its impact on space weather. Today, he will be discussing the X-ray astronomy of the space, sharing insights into the latest discovery and advancements in this vital area of research. Today, we have this unique opportunity to learn from one of the most influential person in this field. Thank you.
Yeah, thank you, Chetan. I will try to share it and then start talk about um, the X-ray. I mean X-ray photons or X-rays electromagnetic radiations coming from the sun. Let me see. I hope you are able to see my screen. Okay, are you able to see my screen?
Yes, sir.
Okay, okay. Thank you. So I'm going to talk to you about X-rays from the sun. I'm sure you would have heard something about how the X-rays are produced, and especially X-rays in the astronomy perspective. I'm going to focus more on the sun itself. I mean, it's only a star of certain characteristics. I will just talk to you about how the X-rays are produced and how do we look at these X-rays photons, and also how do you use this to decipher the physics which is going on in the sun. What you see here is a kind of a collection of four pictures. These are all taken at the same time, but at a different wavelength. What you see here on the left-hand side in the red color is the X-rays, soft X-rays. When I say soft X-rays, the energy is from say less than 1 kilo electron volt to about 10 kilo electron volt, and hard X-rays is anything about 10 kilo electron volt energy range. What you see here is the full disk of the sun, and you see this many of these bright regions, and these are the regions which you see it on the white light, which is visible light, which we know how the sun will look like, is marked here. You can see it here. The yellowish color is nothing but the white light full disk sun, and you see some numbers marked. They are all the sunspot numbers, activity number. So it clearly says that wherever the activities are there, the magnetic activities, which are the dark patches, what you see on the solar visible light, you can definitely see a brightenings in the active regions. And similarly, the blue color pictures, what you see here on top um, uh, is the extreme ultraviolet band image of the sun. Again, it shows the active regions, all these active regions which you see as a dark regions on the sun. You see it as a bright structures which is seen here. Okay, and grayscale, what image what is captured here is nothing but the magnetic fields. That means the strength of the magnetic fields marked in the colors, and so The gray colors are magnetic fields of zero Gauss, whereas the bright and the dark patches, what you see here, they are all highly magnetically magnitude of the magnetic field is very high. So bright ones are the field lines which are coming towards you, and the dark one, the real dark one, is the field lines which is going away from you. So this shows the bipolar nature of the magnetic activities. What you see here as a sunspot, they are all bipolar in nature, and you can clearly see. And those are the regions where you see very high brightenings in the X-ray band. So if you go back to your physics of how the temperatures and the brightness in different wavelength, you would have seen, you would have heard about this um, uh, higher, I mean, wavelength into temperature is a constant, Stephen Boltzmann law. So, which says that if your temperature is higher, the peak of your emission, especially black body emissions, goes in the lower wavelength. So that's why what you are seeing is here is a bright regions, or I mean here they're all bright because the temperatures of these plasma is much higher. So when people talk, when people try to understand these higher temperatures in these regions, it's a kind of a puzzle because what you see in the photosphere is visible light. What you see in the photosphere, which is of the order of a few thousand degree Kelvin, whereas the brightened regions, what you see here, can be of the order of million degree Kelvin. So, so this is the puzzle which people have been trying to address to it. That when a photosphere, which is deeper in the layer for the sun, photosphere is the first layer of the atmosphere of the sun, and then you have above that photosphere you have this chromosphere, and above that you have this corona. What we now know that is the regions which are bright here, which are much higher than the regions what you see in the photosphere. So that means the temperatures at the higher layers of the atmosphere is higher than the lower layers of the atmosphere. While the lower layers is of the order of few thousand degree Kelvin, higher layers can go up to the million degree Kelvin. What is the source of this high temperature is one of the major unsolved problem even today, though there are a lot of theoretical understanding how these, whether such high temperatures can come to the corona. However, we still don't know the real physics, what makes the sunspot hotter, the regions hotter in the higher layers compared to the deeper layers, where it is cooler even compared to the quiet sun regions. So that's one important aspects which both extreme ultraviolet and X-rays gives an important observational clue for you to understand it. Okay. So, so again, this is a combination of multi-wavelength solar image taken from different instruments. All are from space. The the high energies, again, when I say high energy, it's about several keV, maybe tens of keV. They are all marked in blue. You can see that the high energies are concentrated mostly on the regions where you have a very high magnetic field strength, which is the active regions, the sunspot regions. The lower regions are marked in green, so they are all. They also see emissions in the active regions. However, you can also see them in the regions where there is not much very strong magnetic field lines present there. And of course, UV light is the red, which is there everywhere. So this shows that yes, magnetic field plays an important role to give this high energy phenomenon in the sun. And magnetic fields are not only present in the active regions, it also presents in the quiet regions of the solar atmosphere. Uh, the quiet regions, what we think is a quiet regions, is also active in terms of having certain magnetic field strength in those regions. Here is a sun in over 11 years of cycle. You can clearly see that during solar minima, most of the regions of the sun is not very bright, though there are activities wherever you have this magnetic field lines. There are activities which you see here. Whereas during solar max, you see that the sun is fully with active regions, and the solar output in the X-ray band is much higher compared to the solar minimum. Okay, so though we have seen the different phases of the sun, what I'm going to talk and concentrate mostly for today's discussion is solar flares. I mean, though I've told you about the higher temperatures, even when there are no solar flares happen, um, due to certain physics in the sun. I'm going to mostly concentrate on solar flares, so which is a dynamical phenomenon, which is going to tell you about a few dynamics which is happening between the magnetic fields and the plasma, and which is also an important element for our space weather aspects. That is the connections between the sun and the earth. I will, I'll touch upon it a bit more on that. However, it doesn't mean that the quiet sun X-ray observations are not interesting. They are interesting. Just that for the sake of time, I will not be able to go into the details of that. Okay. So what you see here on the right-hand side is a movie of a flare, which is a flare which is I think I feel it is the biggest flare so far what we could record or what we could have seen in our current period. So this happened in 2003, and okay, solar flares is nothing but a sudden release of energy. So, whatever we have seen as bright structures in the solar atmosphere, you can see them, they're all dynamic in nature. So, you can clearly see very dynamical brightening changes which happens all through the sun, especially in the active regions of the sun. So what you see has kind of a magnetic loops. You can see the very fine loops which is happening. So you can see here a lot of active region loops which is going on here. They all actually dynamically changes in terms of its intensity, and you can see that suddenly you start to see as salt and pepper pictures in your CCD camera in your image. Okay, so that happened just before. I'll just run it again. Go back and run it again. You just keep a watch on it. I mean, you see this all these very nice loops, which is representations of the magnetic field lines, which is connecting between the south and north pole, or the bright and dark patches. What you see on the magnetogram, and you would also start to see that they just brighten very fast and then start to go back. And then when they start to brighten, especially when that brightening happens in the line of sight of the telescopes or the observing platform, you would start to see that the flare or the sudden rise in the intensity um, uh, do causes some effect on your observations. It's not only the brightening, you also start to see that, say, for example, this flare, which had happened, okay, after some time, you would start to see them, yeah, so this flare, just after some time, you start to see this salt and pepper picture of that. So this is apart from your sudden brightenings which is happening in the sun. I mean, this events also throws a lot of plasma into the interplanetary medium. When I say plasma, it is, I mean, as you know, plasma is nothing but electrons and protons of equal densities or equal number. So the plasma as such is neutral, but they do contain electrons and protons. So what happens in this scenario is the brightenings, what you see here, what we call it is magnetic reconnections or solar flares, has thrown a lot of electrons and protons or the plasma in the interplanetary medium. When these charged particles comes and interact on your device, which is your camera, which is made of silicon or any of these photon sensing material, they are also sensitive to these particles. So the particles do deposit some energy on the devices. That's how you see this sudden grainy natures which you start to see in these images. Of course, I mean, if the energy of these particles are very high, they can damage the system, and you may not be able to recover the system further. So that we call it as a space weather. And these are the particles when they come and interact with our Earth's atmosphere and get coupled to the Earth's magnetic field, can propagate or can travel up to the ionosphere or lower ionosphere and interact with the atmosphere and produces a lot of chemical changes in the atmosphere, and that's how you start to see these bright auroras in the northern regions, and sometimes it can even come as low as as small the equator as the what where we live in, like in India. The recent big event which happened on May 11th did reach up to the Hanley, where I think they have even captured the auroras. I mean, the different colors what you see in the sky due to that particular event. Here again, two movies. One is again the flares which happened, which produces all this salt and pepper. What I want to bring out it is it's not only the sunspot regions or the flaring regions. You also see a lot of dynamics going on very close to the sun. You can see the plasma moving in the loops of the magnetic field lines. All you see here is a fine scale structures on the sun. They're all the magnetic field lines which are very dynamic in the sun. And these ejected particles, the plasma, you can see it in the chronograph, in the white light band. You can see these ejections from the chronograph, and this travels to very long distances and reaches even up to the Earth and then other planetary systems. That is what this chronograph data which shows from the so. Okay, I'll just quickly go through this history. So this first observations of the flare was done sometime in 1859, which was a white light flare. That means those days we don't have a very high hi-fi instrumentations with a very narrow band filters and other stuff. So people were observing the sun in the broadband, that is in the white light. And usually, white light flare, if you're seeing, that would be very high energy flare, because I mean, we'll come to. I'll tell you how this flare happens and when does the white light flare. You can see it in the further slides. So that is the first time white light flare was observed, and the first time the flare was observed by Carrington and Hodgson, and followed by people started observing them in H alpha. H alpha is transitions the wavelength transitions in the hydrogen band. It falls in 65, 63 angstrom. So people use a filter around 65, 63 and look at the sun in that particular filter. You'll start to see many flares compared to without the filters. There are different source sizes. Ejection of plasma bags and the chromospheric waves is also observed sometime in 1962, and they are all now called as a Morton waves. The flares gives certain kinds of waves, and they are called as Morton waves because it was first identified by Morton. And once people started to seeing in the electromagnetic band in optical, they also started to look at radio emissions, and these all happened during the military radar operations. And once they identified these signals are coming from the solar flares from the sun during some of these military operations, they realized that radio is one of the important band where we can look at the sun for the solar flare and other related phenomena. And they started to interpret the data, and radio emissions are found to be from non-thermal. I'll talk to you about what is thermal and non-thermal. And the emissions can vary several orders of magnitude in this band. Around 1983, in the same period, Forbush noticed ground level cosmic ray enhancements with major solar flares. That means the cosmic rays um, um, started to increase during the solar flares, just before the solar flare. Is also an important observations during that period. After 1950s, when the observations are started using balloons and rockets, that is when a considerable amount of progress was made in X-rays, especially high energy bands, because X-rays or the high energy electromagnetic radiations doesn't reach the ground. It's a good thing for us because X-rays can be dangerous for human beings. So our atmosphere is protecting us for not allowing the X-rays. However, we won't be able to study many of these what you call stellar phenomenon unless you go above the Earth's atmosphere, either using balloons or rockets or satellites. Peterson and Winkler are the first to detect hard X-ray photons from flares. Again, we know that they are all Bremsstrahlung radiations coming from colliding electrons. I will also talk about the physics behind these emissions. And in 1968, a person called Newport predicted that energetic particle may contain the sizable initial flare energy release. This is also called as a Newport effect. I will also talk a bit more about what is Newport effect and what you can do with the existing data of the Newport for the Newport effect. Spectral energy distribution, which is nothing but how the energies are at different waveband, especially in high energies. They exhibits a non-thermal shape close to a power law, and especially when you look at the high energies like anything about 10 kilo electron volt in X-rays, you will see that the spectra is a power law distributions, whereas the low energies resembles of a thermal distributions. And we know that now they are all because of the charged particles gyrating along the magnetic field lines. So the broadband radio emissions, the gyrations of these, both the gyrosynchrotron radiations and the synchrotron radiations, provides us the high energy radiations from these observations. In all doing that, in 1970s, we also see the gamma ray line of heavy nuclei was discovered. That means the energies are very high that these charged particles can penetrate even the atomic atomic level. I mean, for you to get gamma ray line emissions, which are from the atoms, the electrons have to go to the atomic nucleus and knock off the protons from it. So they're all in the MeV mega electron volt ranges, and that is first discovered sometimes in 70s. Finally, thermal millimeter UV and soft X-ray emissions have shown that the flare energy heats the plasma of coronal lobe to temperatures from 1.5 million Kelvin to beyond 30 million Kelvin. So there are loop brightenings. Whatever you saw previously in the movies where the loops are brightening, they are all related both to the density enhancement as well as the temperature enhancement. Such temperatures and non-thermal acceleration acceleration of non-thermal particles suggests that the flare is originally a coronal phenomenon. So that means higher temperatures as well as the non-thermal, which are governed by the magnetic field lines, they are of the coronal phenomenon. It's not in the deeper layers. However, white light flares emit relatively large energies, which means that white light flare can be a process which makes the particles to reach closer to the photosphere. So the current era, we have observations which gets much closer to the heart of the flares, but still miss the primary process, which is we call that as a reconnection process. We also understand that flares couple to the chromosphere in a substantial way and must be understood as processes in which corona and chromosphere form an interactive systems. I mean, of course, as I say, white light flare also couples the photosphere of the sun. So it's a atmospheric coupling which happens during a solar flare. That is what we have to keep in mind. Here are some facts. I mean, if you go to any space weather website or any website where you talk about the light curve of a flare, when I say a light curve, it is the flux of the flare as a function of time. So here you see yeah, a 4-day light curve of flares, which I showed you about the Halloween flare, 2003 flare. You can see that the light curves. This is the soft X-ray band. You can see the colors here represents the wavelength range, which is related to the energy range. Say, for example, 1 keV, 1 angstrom is roughly 12.5 keV is the kind of relations. What you see here is a sudden increase in the flux, which is marked here as watts per meter square. And you can see that sudden increase, the increase can be of the order of, several orders. Say 10 power minus 7 can go all the way up to few tens of 10 power minus 4. So which means the flux from the sun can go several orders of magnitude in a very short period of time. And you can also see more or less a characteristic shape of the flare, that you see a sudden increase and a slow decay. So it is like if you have studied charging and discharging of a capacitor, this is how it will look like. You charge the capacitor, it charges very fast, and then when you discharge the capacitor, it discharges slowly. So that is what you see in most of the flares. Of course, there are flares in the later part of the talk. We'll talk about different aspects of the flare. But most of these flares, you see a sudden increase and a slow decay of the flares. Okay. And when they do that, I mean, you can see that the flares energy ranges from 10 power 27 to 10 power 32 ergs, which is the total energy. That means it is the total energy content during a flare, which is an integrated flux within the flare light curve. And the durations of these flares can be anywhere from a few hundred, I would say. Typically, these rise times, what you see here is of the order of few minutes. With the recent high sensitive observations from our own spacecrafts as well as other spacecrafts, we do see that this can even be less than 1,000 seconds. Typical number, most of the flares will be from 1,000 seconds to 10,000 seconds. And they are in different size scales, 10 power 4 kilometer to 10 power 3 kilometer in height. That is what people say, that it is in the chromospheric or in the coronal regions of the sun. And this table tells you different scales of the X-ray events, what you see. Starting from microflares. Microflares are the flares whose energy is 10 power minus 6 times of the energy of the largest flare, which is of the order of 10 power minus 3, as you can see it here. So the microflares will form somewhere in this 10 power minus 9, 10 power minus 8 band. And then you have these impulsive flares, and then long duration events, LDE flares, and then large scale arcade formation. So they all vary in terms of size. So if I take a flare in a 3D volume and then put them in a 2D size scales, the L is representing the length of that size scale, which varies from somewhere around 5,000 kilometer to all the way up to 1,000, I mean, 1,000 kilometers, 10 power 6 kilometer. And the time scales varies anywhere from 60 seconds, as I told you, to go all the way up to 200,000 seconds. Energy ranges from 10 power 26 to 10 power 32. So that's where this microflares to the largest flare. And they are all seen at a different, they are associated with different events, which we call in solar physics jargons, jet surge, H alpha filament eruptions in X-rays. So some most of them in the jet and surge is seen in extreme ultraviolet, and most of these flares, high energy flares, are seen in X-rays or H alpha wavelength. Now, how does the spectra look like? I mean, I'll spend at least 5 minutes in this particular slide because this is an important slide, which brings out all the physics what we talked about it. I will do it in two manner. One is I will just first concentrate on this right hand side plot, which is a very small cut across portion of the sun where the flaring event happens. So what you see here in this particular cartoon is two magnetic field lines, the south, north and south polarity. I mean, let's say you have two magnetic field lines which are connected by the magnetic field lines. Okay, so these magnetic field lines are marked as the field lines here. So they are all connected, and for some reasons, as the magnetic field lines dynamically evolve, if there is a small regions where you have a infinitesimal perturbation happens in this particular region, the magnetic field lines from the surrounding regions. For example, if I have another magnetic field lines with opposite polarity, which is forming above the magnetic field lines, these two field lines can reconnect, and forming a kind of an arcade kind of phenomenon. So this particular region, which is somewhere in the coronal height, is the regions where the reconnections happens. The magnetic field lines gets reconnected and form two pronged magnetic field lines. You have a field lines which is somewhere concentrated around this particular region, and a field line which is concentrated around this particular regions. So you have these two kind of system which gets formed, and once that reconnection happens, whatever particles which were in this particular region, they get accelerated. So magnetic field reconnections is nothing but the north south of one bipolar gets reconnected to the north south bipolar, and the magnetic field lines get reconnected to the north south bipolar,
Uh, Excuse me, sir. You're not audible and the screen is not shared. Sir, are you in the meeting? There seems to be some technical issues from sir's side. Kindly wait a few minutes. We'll ask him to try to resolve it. Dr. Shankar, sir, can you hear us?
Yeah, can you hear me?
Yes, sir. Yeah, we can hear you now.
Okay, okay. Okay, you can see the slides.
Not yet, sir.
Okay, maybe I'll share it again.
Yes, sir. Now it's visible.
Okay, okay. Shall I go ahead?
Yes, yes. Please continue.
Okay, fine. So I'll start from where I left off. So we talked about the particle accelerations which happens in the reconnection area, and the particles which falls into the solar atmosphere heats up the plasma in it, and the heated plasma fills this loop, and the particle which gets accelerated in the interplanetary medium is a particle which we see with our spacecraft when the particle crosses the spacecrafts. On the left hand side, what you see here is the a kind of a spectra, which you would observe them from say 1 keV all the way, all the way to very high energies of the order of few tens of MeV, and you can
Sir, you're inaudible. Sir, uh, there seems to be some technical.
Okay, so I see that I think you are able to hear now.
Now we are able to hear, sir.
Yeah, I think somehow it's getting unmute. I mean, muted often. So anyway, you let me know as and when it happens.
Yes, sir. Yeah.
Okay, I will share it again. Okay, so these non-thermal particles, when they get accelerated, they emit a non-thermal radiation. So you can see in the spectra, which is the energy versus photon flux, you can see a region up to say maybe around 10 to 20 keV. It is dominated by the thermal electrons, whose accelerations provides the X-ray band, whereas above 20 keV you see a non-thermal nature of the spectra. And when the electrons gets traveled along the magnetic field lines and hits the chromosphere, there are two cases where what we people study is thick and thin target brimstollen. This is nothing but if an electron cannot penetrate the atmosphere, then the atmosphere is called as a thin target because the electron can deposit energies at different layers of the atmosphere and hence penetrate into it. So it's called as a thin target. And a thick target is the electrons cannot penetrate deeper into the layers and hence deposit all the energies at certain height of the region. Okay, so they're all modeled using a power law, say energy power minus gamma, and the gamma is of the order of delta plus 1 and delta minus 1. So here you see some of these power law indexes as the flare evolves during the period. Okay, I also talked about this Newport effect. Newport effect is nothing but I mean what it says is the flare energy is the one which creates which creates your heating and the cooling of the plasma. So the energy deposited in the impulsive phase, where most of your hard X-rays emissions are there, the hard X-ray emissions has to, I mean, can give you what kind of soft X-ray emission which you are going to get. So the Newport effect says the if you take a light curve of the soft X-rays, the flux light curve as a function of time, you do a time derivative of the light curve, you should get a flux of the hard X-rays. So that means if I take a light curve of a soft X-ray and do a time derivative, I should match with the hard X-ray light curve. So that is what is called as a Newport effect. Of course, not all flares follow this particular phenomenon, but most of the flare does behave like this. So this above equation is, I mean, is an approximation that the all the heating and cooling is happening due to the particle accelerations. Of course, all the heating is happening due to the particle accelerations. Cooling by conduction and or radiations during that period is neglected in this particular approximation. Okay, this is the model which I told you that the reconnection happens. The accelerator particles comes and falls and goes along the magnetic field lines and goes to the chromospheric foot point and then start to evaporate the chromospheric regions and then fill these regions with the bright regions of the surrounding. So this is called as chromospheric condensations and the chromospheric evaporations. Talk to you about some of these, which we can do it with our own spacecraft Aditya L1, just to give you a flavor so that those who are interested can start utilizing, start looking at some of this Aditya data together. So what you see here is an active region, which is a bipolar active regions. You can see the magnetogram here, positive and negative polarity, the sunspot, what you see here. And here is the UV emissions coming from the this particular sunspot region. A small portion of the sunspot region is magnified here. So you can see these three active regions are seen here as these three active regions. You can see that the flare happens here, and you see that the flare is not. I mean, the deposition of the energy is not in single place, right? Over time, it gets dynamically moves across, and then start to increase in terms of the in terms of the area. So what people have tried to do it is to try to look at the non-thermal energy from the hard X-rays and try to look at how the UV emissions are captured. So if they take if they take the contours of these bright regions, which you see it during the end of the flare. I'll just run it once again. You see this all this brightening is happening because of the particle which is coming and hitting the chromosphere and heating them up. And as the flare starts to evolve, you can start to see that the magnetic reconnections which happens at different places, and then start to emit the photons in these energy bands, and you will start to soon see them that the flare picks up over the full active regions and gets brightened up. Correct. You can see that the brightening is keep on evolving with time, and the bright loops also will changes with the time. So if I calculate the area of the brightening as it goes higher and higher, that is related to the density of the electron which gets accelerated. So the hard X-ray light curve, which is related to the accelerated particles, and the UV light curve, which is related to the brightening, should go hand in hand. UV, not the brightening, UV the contour area, that means the area of the brightening as a function of time should go hand in hand. That is what this particular plot people have observed with other instruments, of course, the iris as well as the Fermi instruments which looks at the hard X-ray band. Similar thing one can do with the flare of the suit instrument on board Aditya L1. Here, what we have tried to do it is using the magnesium and calcium filters can be used it, and hard X-ray observations are coming from one of our instrument on board Aditya L1 called Helios, high energy L1 orbiting X-ray spectrometer. And combining these two, one would be able to study how the evolution of these aerial brightening in the suit image related to the hard X-ray light curve from the Helios instrument. What I talked about so far is flares in the higher energies. I will just spend a couple of minutes on the micro flares. There are flares which happens in the quiet regions. Of course, they can be associated with a sunspot, or there are flares without the sunspot activities also can be seen. And you can see that there is a gamut of paper which has come in the last 4 to 5 years using this XSM X-ray X-ray solar monitor on board Chandrayaan 2 of our mission. Um, um, and this XSM instrument was sensitive to very low class flares, and hence we are able to get a spectra in the very soft X-ray band, say starting from say 3 to 1 to 10 keV, and try to fit them with different power laws. And there is also another a mission called New Star, though it is meant for the astronomy purposes, and it can also look at the sun when the sun is quiet. And a certain time period, they have looked at the sun when the sun is very quiet in the during the A class period. Okay, so if anybody is interested, one can go through this particular phenomenon. Okay, I'm going to talk another 1 or 2 minutes on the. I mean, these are all recent observations, so I thought maybe of interest to you. What I told you is about the event where the flare is fast rising and then slow decay. It's like a capacitor charging and discharging. Whereas we are also have seen with the XSM data that it's not always the case. There are flares where you have a rise and fall time can be totally different. For example, here we try to characterize this rise and fall time using two parameters. The sigma is the rise time when it goes from one particular position to the peak position, and the tau is the decay time when it goes from peak to a certain period of the time. So something like a 1 over E of the time is called as a tau. The ratio will tell us whether it is steeply rising and slow fall or slowly rising and slowly falling. So this distribution, if you look at it for different flares, is what is seen here, and you can see these impulsive flares. Of course, they are all many more impulsive flares, but there are also flares whose sigma by tau is more than one. So which means that the rise time is no more faster. They are slower than the decay time. It's an interesting cases which we were able to do it with XSM because of its sensitivity. Here you can see, I mean, this to get this data, we had analyzed close to something like a 10,000 flares from the XSM. Now, X-ray observations can also talk about the coronal abundances. Here, I'm talking about this first ionization potential bias. I'll just explain to you what it means. What we have seen in the observation is, I mean, what you see here is the abundances of different species. Say, for example, iron, calcium, silicon, and sulfur, which is present in the solar corona. How is the abundances of them with respect to the photosphere? So when the abundances is one, the coronal abundances is equal to the photosphere. We want all the elements to be closer to the photosphere because the plasma is in the sun, which is in the photosphere. So the corona should have a photospheric abundances because all the plasma in the corona has to come from the photosphere. Whereas what you see here is that there are certain species whose ionization potential, first ionization potential, that's why it's called the FIP, is below 10 eV. So this 10 number is corresponds to 10 eV. 10 eV, if I convert into temperature, is about 10,000 degree Kelvin. So any elements which gets ionized at the temperature of 10,000 degree Kelvin, below that temperatures, they are all called first ionization potential temperatures. Those elements gets enhanced in the sun compared to those elements which are higher ionizations. Okay, so so this is also done with exosome, trying to understand how this abundances varies as a function of the during the flaring time. We can definitely see that the abundances, though they are all high during non-flaring time, during the flaring time it reaches to the photospheric abundances, which is marked as the grayscale here, which reaches to the photospheric abundances during the flaring time. This has certain interesting implications on the solar flare model, and these are discussed in this particular set of papers. So if anybody is interested, they can go through these particular papers. I'll talk about this quasi-periodic pulsations. This is something which we also seen it in the light curve previously, and you can see that this is the light curves shown in different energy bands. 6 to 12 keV is marked as red, and then 12 to 25 is the green, and 25 and above 300 keV is marked in different band. You can start to see that
Sir, you are inaudible again. Sir,
Okay, I'll unmute it. Can you
yes,
hear?
sir. Yes, sir. Now you are audible.
Okay, I'll share it again. Okay, so as you track the loop top, you can see that the plot of the loop top as a function of time, which is marked as star here, you can clearly see that the trend of this loop top tracking clearly matches with the soft X-ray rise curves in here. So it's interesting phenomenon. Though I think it's not seen for all the prominence eruptions, but certain prominence eruptions are seen. So Aditya will be able to do it because you have this suit instrument as well as the soft X-ray instrument Solex. We can do it regularly with Aditya instruments. Here is a case of flare CME. The CME and flare are associated in multiple terms, and this is something which we can do it with Aditya also using the VES instrument as well as the Solex instrument. This will be the first time if you are able to do it with Aditya satellite, doing this with the same satellite. Okay, next I think 10 minutes. What I will do is just to give you a brief about how do we do this data analysis with X-ray observations. I'm going to take XSM as my reference, though the Aditya data analysis is being finalized and the manual is being generated. Until that is ready for disseminations and for people to use it, we one can use this XSM data, which is available now in our Pradhan website. People can go and download the data. I will just go through a few steps of the data analysis in the next maybe 10 minutes of time. I'll have to go to manual so that, okay, I think I can increase the size so you can see it, no? I hope I'm audible and you can see it.
Yes, sir. Yes.
Okay. So there is a manual which you can download it in our Pradhan website. Let me see if I can show you where that website is. So if you go to internet and then say Pradhan ISSDC, you will have a website. You can log in there. Okay, it has now currently it has Chandrayaan 2 and GRASP payload. If you click on Chandrayaan 2, okay, so it tells you what are the Chandrayaan 2 data is available. So XSM data is available. So you can go to browse and download. It'll ask for your username and password. You have to register first, and then use the username and password. So if I do this, sign in. Okay, you will get a different payload data. You can go to XSM and you can see the data available. So this XSM data is a daily data. You can see up to 11th July the data is available. So that means as earlier data as possible you will get from 11th July onwards. It's just one full day of data. You can download this data and unzip it. You will start to have the spectral data as well as the light curve data, which is what we will today we will try to study them. Okay. Okay, so I just so this is an instrument which is developed by Physical Research Laboratory, and that's how the people have put together this manual for you to go through. I have just marked a few places where you need to understand what it is about. So what it says is the solar X-ray monitor is on Chandrayaan 2, and it's observed the sun as a star. That means it doesn't resolve the sun as a star, in the soft X-ray band from 1 to 15 keV with an energy resolution better than 180 eV at 6 keV. So that means that it has a spectroscopic capability with a spectral resolution which is 180 eV, better than 180 eV at 6 keV in the energy band from 1 to 15 keV. Okay, so once you unzip the file, you will have all these files which will be available. The file type, the fits. If you see a name of the file dot fits, that file is the raw data frames, which is the science data file. Then you have this HK parameter file, housekeeping parameter file. This is a parameter file which tells you about many housekeeping parameter of the instrument. For example, the temperature of the instrument, and what you call the count rate of the event, the voltages used in that particular instrument. So it's basically for the instrument people to know whether the instrument is working fine, whether the data where you can believe it and use it. So that's a HK parameter. And then you have an SA file, which is the sun angle file, because Chandrayaan 2 doesn't look at the sun. The instrument field of view, the sun varies in the instrument. So depending on where the sun on in the instrument, in the detector, the sensitivity of the detectors are different. So that is captured in this particular sun angle file. You will know whether the sun is in the center of the detector or in the edge of the detector. Then there is something called a good time intervals, which is a GTA file, which tells you which are the good time interval which you can use for your science data, which are the intervals which you have to be very careful whether you want to use it or not. And then you have a spectral file, which is a PHA file, which is a spectra every 1 second, and you have a calibrated light curve, which is also for the full energy band, which is also every 1 second. And here you can see the XSM is archived in ISRO Pradhan website. You can go into this, and then you have this zip files having the name of the format, contain the level 1 and calibrated level 2 data sets of XSM for a given day of observations. So when you unzip it, you will have these directory structures, XSM data, year, month, day, and the raw file and calibrated files. And these are the files which is marked in this table. So this manual is a very self-explanatory, so I don't have to go line by line. I'm just going to capture only a few parameters which you may have to be aware of it. Otherwise, you can simply download it and start using this based on this manual. It is advised that the users unzip multiple data files at the same location on their computer. so that it will be easier to navigate to data for multiple days of observations using the directory structures. So you create a folder and then put all the data in that particular file for different days. That's what it means. Calibrated products provided are for a standard set of parameters in the XSM data analysis software. The standard GTA include all times when the unocculted sun is within the full field of view of XSM and also with the instrumental health parameters within recommended range. So GTA files is a very important file which you have to use to extract the data which you can use it for the science data analysis. The XSM data analysis software, XSM DAS, and the associated calibration database are made available so that users can generate level 2 products from level 1 data according to their requirements. So you will be able to fine tune some parameters of depending on your requirement. Say, for example, if I want to add, say, 10 minutes of data from starting from T0 to T1, when I do this level 1 to level 2, I can use their software, define my T1 and T2, add the data and create a level 2 data, which then you can use it for analysis, for fitting and other purposes. The distribution of XSM DAS provided to the users is meant for generation of calibrated level 2 data products, such as spectrum or light curves of desired binning parameters. That's what I just mentioned to you. Okay, and there is also an installation. You can have a prerequisite and what other software is needed for you to install and the details of the installation. So I think this is you guys will be able to do it pretty straightforward by looking at through this manual. Okay, so there are certain set of models, which are included in this XSM DAS. I just tell you what each one of them. So XSM GTI generation is a GTI file generated model, which is based on parameters ranges from a filter file. That means, though there is a GTA file available, you can generate the GTA file by using this XSM GTA gen by modifying the filter file. So the filter file, I think there is an example also will be there. Okay, there is a filter file which you can modify, and based on that, you can actually generate a different GTA files than what is available in the packed downloaded system. Then XSM GenSpec, which is again generates the level 1 science data with required parameters. Then Gen LC, which is generating the light curve, and XSM adds multiple spectra files together by specifying the time intervals. Okay, so if you want to, interactively, if you want to do, you just do a XSM gen spec and then define the parameter values in the parameter file with the L1 file and the spectroscopic file, which is the PHA, the spectra type. If you want to integrate the whole day of data, you just say T start is equal to 0, T stop is equal to 0. Then you give this HK file, SA file, and GTA file. You will start to run it. Okay. So here is the flow chart of how this is done. This all level 1 data. So from the level 1 data, you can do the GTA generation, create a GTA file by using a filter file. And then the GTA file can be put into the XSM GenSpec and spectral generation as well as light curve generation, which will give you the spectra and the light curve stuff. So I think it's a straightforward one for anybody to do. And they also mentioned for each one of them what it does. XSM GTA generation. This task finds out intervals of time when the HK parameters and sun angle related parameters are within the ranges specified by a user provided filter file. So these are the HK file, GTA file, SA file, and the filter files. These are all needed for you to generate it. And they also give the filter file format. For example, if you want to define the detector temperatures to be between some value, you define them. Okay. HV monitor, the high voltage monitor, you define them. So usually you can leave that. I mean, you don't need to middle around with this until you have a very good understanding of the instrument. The instrument team has generated a good GTA file, which is good enough for you to start off with the data. You don't have to really middle around with it unless you find real issues with the data for you to look at it. Okay, so these are the filter files which you can use it. And XSM GenSpec, this task generates time resolved or time integrated spectra from XSM level 1 science data for the desired GTA with a required set of parameters. Output spectrum file is compatible with standard X-ray analysis softwares like Expect and ISIS. Please refer to the publication mentioned in the reference in section 1 to learn about calibration of XSM if you wish to use any of the hidden parameters. Okay, the parameters, what you need is the L1 file, the spec file, HK file, SA file, and GTA file. And the spec file will get generated out of that. Okay. You can specify what is your starting time, what is your ending time, the bin size, what you want in terms of it. And you also have to generate the response of your director as an ARF file for that particular duration. So the ARF file which is given is for the full duration. And if you want to specifically generate the ARF file for a duration of T0 to T1, you have to generate them so that the calibration files which you are using is matching with your actual spectral observations durations. Okay, so a lot of parameters which you can play around with. Again, only when you go through each parameters, you will be able to understand it. And similarly, the light curve generation is also is available for people to generate it. With a minimum time resolution of 1 second can be generated for any channel range. Um, then you can also generate for 100 millisecond time resolution for 3 predefined channel ranges. Again, you can play around with it and then create your own light curves for the data sets and for the duration you want. And this software is actually adds the spectra. So if you want to, once you generate the spectra every 1 minute or one second, you can still add the spectra and generate your ARF file for the durations of that. So this XSM add spec gives you that particular detail. In addition to this, XSM DAS has additional Python tools. Is basically to convert the time from XSM mission elapsed time to the UT time, because most of the data, when you want to compare it to the other data, the UT is the standard time which people use it to convert it. So you can either go from XSM time to UT time or the UT time to the XSM time. And they also has a small routine to convert the XSM spectra, which is in the count space, to the watt per meter squared unit, which is what you can, which gives you the flux for that particular event. They also have given a specific analysis cases. You can go through it. I think I will not go dwell into too much because this manual is pretty good for anybody to any starters to start it. So when I had a chance to work with some of these IIT Bombay students who were all BE, BTech type of students, they just went through this manual and they were able to generate their own light curves with it. Background spectra is very important because the background in the X-ray band can come from many sources. Even the particles can introduce background. So background is an important element to generate it. There are multiple ways of generating the background. So usually the normal way, what the solar physicists to do is just before the flare, you take a certain duration of observations as your background spectra. So since you are only interested in change of parameters during the flare, you can assume that the spectra what you get just before the flare is not of use to you. So you take that as your background and subtract it from the spectra generated during the flare, and then fit them during the flare. So that is what usually we do it. Of course, people do try taking background during the quiet sun period, or during the period where the exosome looks at a blank sky, which will give you a lot of the other background generated instrument background information into it. Okay, so once you get the spectra, there is a package called expec and ospecs, two different packages. The expec package is usually used in astronomy. I think probably in the morning lecture you would have heard about this expec package. You can port this spectra into the expec package and start to use the expec package for your analysis. That is also mentioned here how to do it. And there is another package called OSPEX, which is specifically for solar observations, which is based on ideal based software package. So you need to have an ideal version 8 plus on a 64-bit platform if you want to use the OSPEX. Of course, Expect is a free package available free to download. So most of the people start to use this Expect package, not the OSPEX. I think that's all I have from my end to it. So if anybody is interested, um, I would request them to just download 1 day of data and just go through this manual and start generating the spectra and the light curve, and play around with the billing, time durations, and other stuffs, and try to look at the spectra, look at the light curve. You get a fair amount of things you can get it. So here is a representative of once you go through these procedures, how the spectra will you will be getting it. Okay, I will not go into the analysis with those specs. So, and then once you are able to generate the spectra and the light curve, then it's your imaginations how much you want to do, and what more data what more science you want to do it with from the data is up to your imaginations. We can all help you, and I mean, of course, there is a set of people in PRL. I think both Mithun and Santosh, you can email it to them if you have any issues. They will be able to address it, and they are also works in this particular area. You can even contact them if you want to work along closely along with me with them. And of course, you can contact me also if you have any issues with this particular XSM data. Aditya, data will soon be available. The Solex instrument is very similar to XSM, slightly better sensitivity than XSM. So that data also, once available, will have a similar manual for you to go through that particular data set. I think with that, I will stop here, and if more discussions are needed, I am open for any discussions. Thank you. Thank you very much for your time.
Thank you very much, sir, for this intellectual session. I'm sure many of us learned great things. We greatly appreciate your time and dedication for it. Now the participants may ask any questions they have in the chat, or like we can unmute them if they want.
I'm not seeing any chat, any questions.
Yes, sir, there doesn't seem to be any question. All right. Thank you, sir, for thanks again for this session.
Okay, okay. Thanks a lot. Thanks for your time
Yes, sir.
too. Okay, there are
Sir,
some.
we have a question.
Yeah. Okay, let me just go through it. Okay, why are logarithmic scales preferred over linear while analyzing most data? Um, okay, so if you are talking in terms of the spectra, I mean, as I told you, the non-thermal electron spectra, what you get is power law. So power law means the brightness or the flux is proportional to exponential of minus delta, which is the power law index. So to make it linear, you just do a logarithmic, then it will come in the linear. Then you can just simply fit a linear plot to get it. If you talk in terms of the light curve, if the intensity drastically changes, exponentially changes, typically the flare intensity changes very drastically. To cover a large orders of intensity into a single plot, if you do it in the logarithmic scale, it gets visualized in much better sense than in a linear scale. So it's a good exercise which you can do. You download a data, 1 day of data where there are flares with XSM data. You just plot them in linear and logarithmic scale. You will definitely see the differences in it. In the linear scale, you will see only the flare durations, whereas in the logarithmic scale, you will see any variations even during the quiet period to all the way in the flare durations. That's because the log scale captures large variations in a small linear dimensions. That is where we go for log scale plots. Can magnetic field lines of the sun theoretically be controlled in order to prevent unprecedented flares? It's a good question, and of course, it is not that easy to control any magnetic field lines. To control a magnetic field lines, um, um, you have to have certain forces which is much higher than what you can control. So um, I mean, if you look at solar atmosphere, it's not only the magnetic field lines, it is the magnetic field lines and the plasma. The interactions defines all your dynamical events which you happen. Say, for example, the solar flares is not only the magnetic field lines. Say, a magnetic field line reconnections without any particles will not give you this sudden emission in there. So it is mostly the particles which gets accelerated, and which is the one which is causing this. So one way for you not to get affected by them is to somehow evade those particles. So you take a precautionary measure that if such particles are coming to you, you can deflect them using a magnet, for example. People do that. I mean, so for example, some of these GOES instrument, what I showed you, since they are also sensitive to particles, what they do is they keep a magnet in front of their aperture, so that the particle coming towards the instrument gets deflected by the magnet in the instrument. Only the X-ray photons enters into the instrument. So there are ways to correct it, but you won't be able to control the sun's magnetic field because they are in a totally different um, uh, strength as well as totally different field lines. Can the solar heating problem solved by Aditya L1? I mean, the solar heating problem is not a new problem. It is a problem which is known from decades. People do have solutions for it. So I can put it this way: we know that the magnetic as well as the plasma nature of the sun can generate enough energy to heat the corona. What is missing is the how this energy gets deposited in the corona. Why is it deposited in the corona? Is the one which is missed. And if you are able to get a good data of looking at some of the waves driven heating and the reconnection driven heating, this is something which we will be able to address it. And of course, this requires a lot more theoretical understanding, lot more modeling before we can be sure that this can be addressed. What causes the magnetic field lines to break and rejoin? This is basically um, uh, what you call the intermittent reconnections. What we get is because of the flux emergence, which is I mean, if you have a sunspot and suddenly flux emergence are coming in the region of the sunspot, the new fluxes can get merged with early already existing fluxes due to the dynamical nature of the magnetic and plasma parameters in the surfaces. That is how the reconnections start to happen. Uh, what is the reason for it, and is there any theoretical explanation? I mean, for the heating, I mean, as I said, there are theoretical explanations. The theory is, I mean, basically the magnetic field which gets moved around by the convective flows below the surface of the sun. So the magnetic fields on the sun, which is anchored in the photosphere, below the photosphere, you have this convective plasma motion. So the magnetic field gets buffeted by the plasma motions, and hence the magnetic field. If you assume the magnetic field lines as a rubber band, if you buffet the rubber band by moving, or even a string, if you move the string, a kind of with the string is attached to one end, a kind of a wave will start to set in. So this wave can carry the energy from the deeper layer, the convective layers. That energy can carry it all the way up to the chromosphere and the corona. Okay, and people have calculated how much of the energy which it can carry. That energy, what is available in the convective layer, is more than sufficient to heat to the level of million Kelvin, or tens of million Kelvin. That's not an issue. The issue is as the mechanical energy, as the energy gets transported from the deeper layers, convective energy gets transported as a mechanical energy to the higher layers. The mechanical energy has to be dumped in the corona as a heating, as a thermal energy. That is the phenomenon which is still not fully understood. So people are trying to understand that particular phenomenon by different types of observations. During reconnections, just like the particles which are pushed out affect the space weather, is there any effect of the particles which fall back into the sun? So all the heating, the heating and filling of the loops is all due to the particles which goes back into the sun, which gets interacted with the higher density medium, and puts its energy into the kinetic energy of the particles in the deeper layers, plasma in the deeper layers. That is how the heating of the plasma happens. And then the heated plasma then moves along the magnetic field lines and forms the coronal loops, what you see as a um, uh, coronal loops. As far as the surface is concerned, I mean, the many of the flares, the particles doesn't have enough energy to go all the way up to the photosphere. If it goes up to the photosphere, definitely you will see a white light flare, which is the first flare which is seen by Carrington in 1859. High energy particles can reach down to the photosphere. And since these particles are high energies, they can ionize the photospheric plasma. And some of these ionized emission lines or the absorption lines, you would start to see it during that process. So far, I think what we can see that the solar activity I mean, slowly will slowly decay, because as the star evolves, you know that the magnetic activities also will start to decay. I mean, in other words, if I want to put it in other words, with respect to other stars, if you look at some of these young stars, the young stars can be, I mean, very active. The magnetic fields of young stars will be very much higher than what we see on the sun. So young stars will have very high energy particles accelerations, which can change the atmospheres of the stars. And of course, Sun would have gone through it, and I mean, it's not only the stellar atmospheres. Suppose if you have planets surrounding it, so all these particles which are coming and getting deposited on the Earth, for example, do provide energy for the our atmosphere, which can escape. For example, if a very high energy particles comes and hits our atmosphere, provides the energies to some of these atoms, say for example sodium or argon atoms in our atmosphere, they gain kinetic energy, and they can escape the sphere of influence of Earth by the gravity. If it has enough energy to escape the Earth, it can escape. So the evolution of the atmosphere is also governed by these flares. So there are theories for our own solar system. We know that Earth, Mars, and Venus, these three planets are formed at the same time, the same environment. But if you look at how they are now, Earth has a good atmosphere and magnetic field where people can live. Mars doesn't have Mars have a very thin atmosphere, no magnetic field. Venus has a very thick atmosphere, but it's full of sulfuric acid. How is it formed? It has some answers to the early evolution of the sun. Though all three planets are formed at the same time, because of the distances, because of the kind of energetic particles which it would have seen, the evolution would have been totally different from these three planets. So it's not only the sun which gets affected; it also gets affect the other planets. So there are this community of exoplanetary people. Now they are looking at the star-planet interactions and trying to understand how the planet would evolve over time from the exoplanetary system. So it's an star planet interaction is a new area of research which is gaining importance because more and more exoplanets started to discover, and more planetary systems are around the stars are started to discover. The statistical data which is available for you to study the star planet interaction becomes more and more, and many of these puzzle what we have been looking at with our own solar system can be addressed by many of these exoplanetary systems by looking at them, because you can capture them at different stages of evolution, like how we capture these stars at different stages of evolution by looking at the HR diagram. One should be able to capture them exoplanetary evolution at different stages of its evolution, which will give us an overall clue about how the planetary system as such evolves in our universe. I hope I have answered most of the question. Oh, okay. What happens to the sun during the shifting of magnetic poles? Okay, this is the stuff which I have not covered, but I'll just try to give you a very brief on this. So as you see the solar magnetic field, I mean the sunspot, they have this 11-year solar cycle. That means the number of sunspot goes up and comes down over the period of 11 years. And the sun also flips its magnetic field. The north and south fields gets flipped every 22 years. I mean the cycle for that is every 22 years. That means I mean today if the north pole, I mean the north of the sun has north pole. After 11 years, the north of the sun will have a south pole, and after 22 years, the north of the sun will become north poles. What happens, as I said, is the sun is formed as a bipolar region. So you will have northern hemisphere and southern hemisphere of the sun. In the northern hemisphere of the sun, you will have a bipole, and similarly in the southern hemisphere of the sun, you will have a bipole. So what we have seen is the bipole when it forms. You have a leading polarity and you have a following polarity. A lead polarity and a following polarity. Always the lead polarity is opposite to that of the the polarity of the poles. Suppose if my north pole has a northern polarity, the leading the sunspot's lead sunspot will have a south pole, whereas the following sunspot will have a north pole. So as the sun evolves, this leading polarity will slowly goes to higher and higher. Uh, I mean, it will start to decay. When the leading polarity start to decay, some of these magnetic decay fluxes gets transported to the poles by what we call it as a meridional circulation. There is a small layer below the sun where there is a flow, which is called as a meridional flow, which takes all these magnetic field lines from the equator to the poles. So as the leading poles has an polarity which is opposite to the polarity of the sun, as the leading pole goes to the polarity of the poles, they will start to what you call um, uh, reduce the polarity of the poles. So slowly the north pole gets connected with the south pole coming from the equator, and the polarity will start to go to zero. And this, along with the dynamo actions in the equatorial plane, is the reason for the polarity flip over the 22-year cycles. So this is something which, if you are interested, you can read through the details of how the dynamo actions happens in the sun, how the sunspot is forms, and how the sunspot is decaying. So they're all interconnected very well, and there's a lot of interesting physics which comes in there. I think that's my answer for that. Okay, thanks a lot for you guys, and thanks a lot for spending almost 2 hours with me. And it's my privilege and my happiness that I'm able to give what I know a little to you. And I hope I have motivated most of you guys to look at some of the X-ray aspects of the sun. Thank you. Thanks a lot.
Yes. Thank you for your kind words, sir. Thank you.
Bye bye.
Okay. Thank you everyone for joining us today, and stay tuned for tomorrow's sessions. We'll soon send you the links. Thank you.